Hi everyone, this is Emrah Turgut. Today we will continue chapter 21. Today we will learn about RC circuits and more problems about the circuits and resistors and the batteries. So RC circuits, you can get it from the name. We combine the resistor R and the capacitance and sometimes the battery. So for example, you can see such circuit, but at the beginning, the switch is open, so there's no current passing through, and the capacitance is empty. What happens when you close it? Then you start to pass the current along and through the circuit. So because at the beginning capacitor doesn't have any charge and zero potential, the initial current is going to be V or epsilon divided by R. So whenever you close the switch, the capacitor doesn't have potential, and all the potential is going to be on the R, and the current is going to be epsilon divided by R. I assume no internal resistance. But right after that, you start to charge the capacitor. Capacitors start to have a potential accumulate on it, and it will be against the battery. What I mean is the current is going to go this way, right? So and then this side is going to positive Q, and this side is negative Q. And let's say at any point you have a potential VC, and if you write the Kirchhoff law, loop law, let's say and you have plus epsilon, and you are going to the positive to minus side of the capacitor, so VC, and the potential is going to drop on the resistance as well, I times R. Then as you see, this VC is going to be epsilon I times R. As at the beginning, you have zero potential on the capacitance, and all the current, all the potential is going to be on the resistor. But as time passes, the capacitor is going to be filled, right? But you see that the current is going to decrease. So current actually the filling speed of the capacitor. As the capacitor has a potential, the speed of filling is going to drop. So that's why you see a decrease in the speed of the filling. So at the beginning, the increase is fast because the capacitor doesn't have much charge and potential. So the current is large. But as you go high and high, in the more charge and more charge, then at the end, the VC is going to be equal to the epsilon, and the current is going to be zero because the capacitor is filled and there is no current can go through. There's no current going through, and the capacitor is full. You cannot take any charge, no charge movement anymore. So that's the time close to infinity. After a long time, the capacitor is filled, but and at that point the current is zero. So this is the potential on the capacitor. And if you try to do some you try to calculate the potential on the capacitance, and using some calculus, you can reach this equation. This is the kind of exponential type of change. At the beginning, you have high speeds, but later on, as the capacitor is filled, you have slow change. And for example, you can look at the processes at the time equals 0. t equals RC, and t equals infinity. For the 0, you have epsilon 1 minus e to the 0. E to the 0 is 1, right? And it will be 1 minus 1 is going to be 0. So potential, let me do this way. VC is 0. That makes sense because the time 0, the capacitance is not, doesn't have any charge. So at RC, epsilon 1 minus e to the minus 1, because RC divided by RC is 1. And at this point, VC is going to be, actually here it's shown 0.63 epsilon. At infinity, so e to the minus infinity, x is going to be 0 because you can write this in terms of 1 over e to the infinity. E to the infinity, e is an, actually, let me tell you, this is a natural logarithmic number. It's a 2.67 something. And when you take the infinite exponential, it's going to be infinite, so 1 over infinite is going to be 0, right? So it's going to be 1 minus 0, and VC is going to be epsilon. So most important part is this time constant, RC. So the how fast you can fill the capacitance depends on the capacitor and the resistor. So let's say if you have a small resistor, then the current is going to be large and you can fill faster and time constant is going to be slow. Then the capacitance, if it's low, it's easier to fill, then the time constant is going to be low. So this type of questions can show up in the exams. It's not too much mathematics, but what is the relationship between the time constant and the resistance, capacitance, and etc. So let's say, and this is in another example, you have capacitance field, some charge, and the circuit is open, it's connected to resistance. Whenever you close it, the capacitance is going to be emptied through the resistance. And let's say the potential on VC is going to be equal to I equals R. But here, like VC is, that depends on the time, I depends on the time, R is constant. So as, okay, the VC is going to be Q divided by C, right, on the capacitance. But as you apply the charge, the Q is going to change, the current is going to change, so it's related to each other. So at the beginning, you have more charge, it's filled, and more capacity, more potential, and you have a large current. But as you empty the capacitor, the potential is going to be small, and then the current is going to drop. So like the speed of discharging is going to be slow, is going to slow as well. So that's why you have such exponential function. So when you have a time at RC and the potential on the capacitance is going to be V naught epsilon RC divided by RC, V naught e to the minus 1, or you can call VC E naught divided by E. So, and then the potential is going to be 0.37 volt V naught at that time constant. So you can analyze this. If you, at 0 time, you don't have any current, so the capacitance filled. The charge is Q naught, and the potential is V naught. Say we did that for RC at infinity. At minus infinity, you will have, it's going to be 1 over E infinity. right? It's going to be infinite, so you divide by Q naught by infinite number and you will get 0. So at time infinity, like very long time, the Q is going to be 0 and the potential is going to be 0 as well on the capacitor. So we have one example problem. You have a capacitance 0.3 microfarad and you have 20 kilo ohm and the battery 12 volt. What's the time constant? Time constant, we usually show tau, it's RC, and the unit is going to be seconds, right? When the unit of the time constant is second. You have 20 kilo ohm and times 0.3 microfarad. Then you have 6 10 minus 3 seconds, 6 milliseconds. What's the maximum charge on the capacitor? So it doesn't ask when it happens, but the maximum charge is going to happen at the infinite time, right? Then the Q is going to be C times V. At the infinite time, the potential is going to be 12 volts. .6 microcoulomb. See what's the maximum current and the current. What's the maximum current and the current when the Q is half of the maximum. So the maximum current happens at time equals 0 because all the potential is going to go through the resistor. The capacitor is not applying any opposite potential, right? So the I max is 12 divided by 20 kilo ohm. So this will be 6.6 milliamp, right? And when the current, and the question asks current when Q is half of the maximum. So actually this is not very complicated. You don't have to do this exponential functions. Think as a, when the Q is maximum, the potential is 12 volts, right? On the capacitor. And when it's half of it, it means 6 volts. In this part, the capacitor is going to apply minus 6 volt into the circuit. You have 12 minus 6, and if you divide by the resistor, it's going to 0.3 milliamp. How much time is needed to get 99% of maximum charge? Okay, so Q is Q naught 1 e to the minus t divided by RC. So this is the correct or full representation of the charge as a function of time. So it asks the 99% of the charge, which means 0.99 Q naught equals Q naught 1 minus e to the e RC. Okay, you can cancel the Q naughts. You have 0.99 1 minus e to the t by RC. This means the e to minus t divided by RC equals going to be 0.01. Now, what you have in the calculators, you have a natural logarithmic function. So which means that, this is a logarithmic function. Let me explain what the logarithmic means. So you have 10 to the 1 equals 10, 10 to the 0, 1, 10 to the 2, 100, 1000, etc. If you do logarithms in 10 base, okay, log 10 base, say if you do 100, it will be 2, because when you log 10, 100 is going to be 10 to the 2, and what you do is log 10 and 10 is going to cancel, and you will just have 2. Same here, like logarithmic e to the 1 is going to be 1. Log e to the 2 is going to be 2. So if you apply this into the function, let's say logarithmic on the both sides of the equation, then you can simplify this. The left-hand side is going to minus TRC, log e 0.01. Then T is going to be minus RC log e 0.01. So we know the RC is 6 milliseconds, right? Minus 6 milliseconds. Let's calculate this logarithmic e using the calculator. I can find the calculator. So you have this ln, that's the logarithmic. And we are trying to do 0.01. This is going to be minus 0.46. Minus 0.46. So then this will be 6 times 0.6, 27.6 millisecond. So in 27.6 millisecond, 99% of the capacity is going to be filled. Now that we come to the point when we connect multiple batteries in series or parallel. So you can use Kirchhoff's law to find the current. For instance, here you can follow this path from A to A. You have 0.5, it's a positive, minus small r. And you have the second battery. And you come to point A again, and you can find the current. So in rule of thumb, like you can, in terms of, what you can do is you can see in terms of math, you can simplify this by 3 minus I to R, right? And you have this capital R. Now you can make an equivalent battery, then this will be just summation of potentials, like 3 volt and 2R, and let's connect to capital R. When the batteries are connected in series. So when you have parallel batteries, and you can apply the same Kirchhoff's law, and depending on the problem, you can use different strategies. But what you need to be careful is, so when you have I current here, the battery is gonna supply I over 2. So the potential is going to, the potential is gonna change on the resistor, because you will, let's write the Kirchhoff loop for 1, right? So you have positive 12 volt minus I over 2 times R minus I capital R. So, I mean, you can write it in the other way, but it's going to be the same. What's important is the potential doesn't change, but you can apply more current through the system when you connect them in parallel. When you connect them in series, you will apply more EMF. Yes. Okay, I mean, there's not much to talk about. Actually, this is just how you construct the parallel or series batteries when you try to find the current. Now we will see some example problems. So we have a circuit, the junction. The current is split to I1, I2, and I3 on 1 ohm, 2 ohms, and 3 ohms resistors. And which one is correct? You can pause and solve. Okay, when they are parallel, the critical thing is the potentials are gonna be same, right? Delta V1, delta V2, delta V3. So this is wrong. Okay, then if you try to find I1, you can do I1 times 1. V2 is going to be I2 times 2. V3 is going to be I3 times 3. So what you see is the I1 is going to be larger. So you can make up a number. Let's say if I3 is 1, I2 must be 1.5, and I1 is going to be 3. So what you see is when you have a parallel resistors, the current is going to prefer to go to lower resistance, which actually makes sense, right? Until you see the same potential. That's what's happening here. So A is wrong, B is wrong, and the answer is going to be D. I1 is larger than I2 and larger than I3, and they're all larger than 0. When S1 is closed and S2 is open, the voltmeter shows V. If S1 is open and S2 is closed, what would be the voltage on the voltmeter in terms of V? So this question can look weird because of the connections, but actually you can simplify that. First, you close the S1 and open the S2. So let's simplify this circuit, or write in a more understandable way. So you have a battery. Okay, now you split into 2 arms, but S2 is open. So in the first place, S2, this resistor doesn't have any current. So all the current goes through R, and this is where you connect the potential, like the voltmeter. And here you split the current into 2. And current here goes through this way, right? Because S1 is closed. So R, and you have R here. And they meet again here. Okay, this is the first case. In the second case, S1 is open, S2 is closed. In this case, the current is going to be split into 2. And it's going to go this way, right? And you will have 2 resistors on that arm. and they will meet again. And the question asks, like, what's the voltmeter value in this second case? But at the end, don't forget that this current, this resistor doesn't have anything. Everything is gonna go this R. Okay, this would be the second configuration when you close the S2 and open the S1. So if you look at, they are symmetric, the equivalent resistors are gonna be the same. So you can do actually, like you can do the math, but just looking at this configuration, you will have the same circuit, and R equivalent 1 is going to be equal to R equivalent 2. So it has the same current in the main R. Okay, if you have I in the main currents, then the potential at the beginning is going to be I times R. For the second one, now we need to figure out how they are gonna split to this I. Okay, the purpose is, let's say you have I2 and I1. I1 plus I2 equals I, the main current, right? And because the potential is gonna be same, 2R times I2, right? I2 goes through 2 resistors, equals R times I1. So I1 goes through 1 resistor. So then you say that 2I2 equals I1. Then if you plug this in here, I2, 2I2 plus I2 equals I. Then I2 is going to be I divided by 3. So what you see is here, the big resistor, like 2R, is going to take third of it, and the single R is going to take 2 of the third of it, 2I divided by 3. So 2 of the third of I. So, and the potential at the end on that resistance R is going to be R times 2I divided by 3, 2 over 3 IR. So IR at the beginning, it was defined as V, right? Then the potential at the end is going to be 2V over 3. Okay, this is one of the exam or homework problems from the last year. We have 3 batteries are connected to a resistor R, as in the figure. If the voltmeter shows the value epsilon, what's the ratio of capital R divided by R? So the batteries have epsilon EMF and the small r internal resistance. Okay, so this is again a little bit complicated in terms of understanding at the first look, but you can simplify them. Capital R, then you have 2 arms. You have this battery, you connect to resistor again. So if you write a loop rule for the Kirchhoff law, let's say you have I, no, it's going the other way. So the current is gonna go this way. So you see that you have 2 arms and they are identical. So they will share the current I over 2. So you can write this loop. It's a conservation of the energy for the Kirchhoff's law. Let's you start from here. You have plus epsilon and minus I times small r, because I'm going along the current, that's minus I times r. And you can pick any way you want, doesn't matter. So epsilon and minus I over 2 times r, because the current is I over 2, and I capital R equals 0. Then the potential is on the resistor is epsilon. Actually, this is what I given the question, right? I can use that later. You have a 2 epsilon minus 3I small r over 2 minus I times R0. So then you have an epsilon I times R. I can plug that in here, 2 times I times R. Then you have 2 minus 1 is going to be 1 IR minus 3I small r divided by 2, sorry. It's going to be 2. And will be 0. Then you see the I's are going to cancel, and you will have R equals 3 over 2R, and the capital R divided by R ratio is going to be 3 over 2. So we have another problem. So I will skip this. This is just another application of the Kirchhoff law. It's actually asking what's the current or something about which one is correct or not. And we have the last question. This is one of the exam problems from the last year. It asked, using the Kirchhoff's rules, which of the equations below is valid for circuit shown in the figure above? And this is kind of typical. You expect, I mean, not too much math, but the checking which one is correct. Let's write the Kirchhoff's junction and loop rules. So you have I1 incoming and I3 incoming, and I2 is leaving at that junction. So for the loop, we can try this and this one. Let's look at the equations here. I don't see anything close to the first one. And then loop 1 is going to be, let's start from here and going into that direction. It's going to be plus 2 ohms times I1, because I'm going opposite the I1, minus 1 volt. Then I'm going to opposite I2. It's going to be plus 2 ohm I2. It's going to be positive 4 volts, 0. Let's simplify this. 2I1 plus 2I2 plus 3. So let's see if we have anything like this. Actually, you see that it's E is going to be same. So then the answer is going to be E. So if you don't see it, like, you have to write the other one, and then the one of them is going to show the one of the options in the questions. So that's all about chapter 21. So let's summarize. We learned about parallel and the series resistors and how we can calculate. And we learn about Kirchhoff's laws, like 2 rules, junction rule and the loop rule. And we learn about RC circuits. We learn about some small, like Wheatstone bridge and measurement of volt and current, potential and current. And that's all for chapter 21. See you for next time.